So welcome back, everybody, to the security stream. This is the last session of the day in terms of the security track. But the day is not yet done because directly after this, we've got the keynote. So that's Mark Wilson actually doing the closing of the conference. So if you can join us for that at 5:30, that would be great. But right now, I'm going to hand you over to Mike Casper and Scott Woolley from IBM. And I think this is your first time presenting at GSE, is that correct?
Yes, it is.
Wow. So very warm welcome to the GSE family. You're most welcome.
Thank you.
And I'll hand over to you. Thank you very much.
All right. Thank you, Jamie. Yes, I'm Scott Woolley, and the other guy on the line is Mike Casper. We're part of the IBM z/OS Secure Engineering team here in Poughkeepsie, New York. Our team's mission is to find and help to avoid exploitable security vulnerabilities on z/OS. Now, Mike and I are co-presenting this session, so I'll start with a review of system integrity and vulnerability patterns that we find in authorized system services. And after a break for some questions, then Mike will follow up with a discussion of some less obvious and even surprising problems that we've encountered, followed by another opportunity for questions. So how many lines of code does it take to compromise all security and integrity on the z/OS solution stack? Yes, you knew it. The title already gave away the punchline. One. So before I tell you about the kinds of vulnerability patterns that we encounter, I'd like to review some terminology with you. And I know that there have been some sessions immediately prior to this one. Rob Scott gave an excellent overview of secure engineering and offered plenty of good advice when developing authorized code. And Brian Childs also discussed a wide range of secure engineering topics, somewhat centered around his discussion of the Authorized Program Facility, APF. So even if you've heard this before and you're very familiar with it, please hang on a bit, because by the time that Mike delivers his part of the presentation, you are bound to hear something new. Okay? What is system integrity? Okay, well, back in 1973, IBM published the first system integrity statement for MVS, and it was subsequently updated for OS 390 and z/OS, and it has stood for over 4 decades as a symbol for IBM's confidence in and commitment to the z/OS operating system. So the statement says that in z/OS, there is no way for an unauthorized program to bypass store fetch protection, bypass racket protection, or obtain control in authorized state. And if any IBM system integrity problem is reported to IBM, IBM promises to take action and resolve it in the specified operating environment for supported releases. There are similar integrity statements for ZVM, ZPTF, and ZBSE. Now, what does authorized mean on z/OS? We say code is authorized or system authorized if it's running in supervisor state. Operating system code generally runs in supervisor state in order to execute the various privileged instructions that it needs to manage system resources, users, jobs. Conversely, we say that regular user programs run in problem state. Code is also considered authorized if it's running with a system key from 0 to 7. This is distinct from user keys that are 8 through 15. And code is also authorized if it's a job step program loaded from an APF authorized library, and the module is linked to AC1, or any module that is loaded from an APF library and is called from another APF authorized module. So if you have any one of these 3, then you can gain the others. So an authorized An unauthorized program cannot directly execute privileged instructions that might compromise system integrity, but it can call certain authorized services that may inadvertently do it. And so much of my testing focuses on the boundaries between unauthorized callers and authorized services. What kinds of services are we talking about? Well, we're talking about SVCs and PCs. Some of them may be restricted for only use by authorized callers, but they can be defined for use for being called by unauthorized callers, and I'll talk to you a little more about that in the PC case later on. Programs in the APF library concatenation. And as I said before, they need to be linked to AC1 in order to be run authorized. Programs that are defined in the program properties table can be assigned an execution key. So you could assign a system execution key to the program, and it would run authorized there. Interestingly, that program must also reside in the APF list, but it doesn't need to be linked to AC1. And in the z/OS Unix space, there are set user ID and set group ID kinds of programs. Set UID and set GID can be used to elevate the privilege of a user by executing a program with the permission of the owner or the owner's group. For example, if the owner is a super user, then it would have all the kind of root privileges in the Unix space. You can set file permissions, and you can even set the APF authorized extended attribute bit to make various programs run authorized. In this presentation, I'll focus on the boundaries between unauthorized requester and an authorized PC or SBC service. I'm not going to talk about services that only can be called by authorized programs because, well, if a malicious program has already gotten into authorized state, well, the game's already over. So let's look at the parameters that are passed by an unauthorized caller. They cannot be trusted. So I have that listed in red over here on the screen, and you'll hear it all the time. You've heard it probably many times before. You cannot trust the parameters from an unauthorized caller. And so what we do is instead of copying them directly, like with an MVC, we have specialized instructions that help defend against untrusted parameters. You'll recall that architecturally there's a storage key associated with all storage, and it helps control reading and writing to that storage. And the system matches your execution key with the storage key to determine whether or not you can read or write storage. And we have these safe copy instructions that you can use instead of a vanilla move character. We've got a move character with key, we've got a move character with source key, a move with destination key, and a move with optional specifications. For all of those, you can specify the key you want to move with, and that key would be the key of the caller. And we do this to ensure that an authorized service does not cause the service to read or write from storage referenced by an unauthorized caller that would not otherwise have access to that storage. Why mustn't you read or write the caller specified storage while running a system key? Well, it may not actually be user key storage, right? The user may have accidentally or intentionally passed in the address of system key storage, or the storage could have changed from user key to system key, and this is the time of check to the time of use problem. When the service is first called, it could have been user key storage, and then subsequently that address could then represent system key storage because the original storage was freed and reallocated with system key storage. So it's good to note that whenever we use these special instructions to copy the caller parameters, we need to do it not just once, but every time that caller storage is referenced. Now, you might say to yourself, well, my service doesn't write out any storage or even return data to the caller, so how could there be a security integrity problem? The answer is that the service might be interrupted near the time it's accessing the system key storage. So these are the kind of interruptions that can happen that could be scheduled. We've got asynchronous ABINs, dispatcher interrupts, timer interrupts, TSO attention interrupts. And so if you interrupt the service, what information might be divulged? Well, you might be able to read register values. You can read the status information, like the condition code set in the PSW. And with this information, you can sometimes deduce the action of a program by these results. So let's start with our top 6 vulnerability patterns that we see. Why do we need to know these kinds of patterns? We want to be able to recognize them because we want to prevent malicious attacks from things like, well, you remember the Heartbleed bug back in 10 years ago. We want to avoid malicious software, ransomware, you name it. Pattern number 1, the unintentionally authorized PC. When you register a PC service, you use the etdef macro. And an important parameter on that macro is the AKM parameter, which specifies which PSW key the caller must be running in order to invoke the service. So we've got an example here that says AKM 0, and that restricts the PC usage to callers that are only running in key 0. Another thing we see sometimes is the AKM 0 through 15, and that says a caller running in any of those registers is allowed to invoke the PC, authorized or unauthorized, right? So remember that, if you've been coding, say you coded a PC routine before, and you go to create a new one, don't just blindly cut and paste the etdef definition from what you used before, because the prior one might have only been intended to be for authorized callers. But here, if you specify 0 through 15, that would allow any caller to call it. So it's a good chance that you'll have some kind of exposure there because the code wasn't written to expect unauthorized callers and protect against them. Pattern 2, the untrusted params, untrusted registers. So register 1 is often used in ZIO's programming convention to pass a parameter list address, but there's no guarantee. A caller may mistakenly or intentionally pass the address of a system key storage area. So you need to make that safe copy using one of the instructions previously discussed. Now you may be used to seeing register 13 used as a save area address, but a PC is not the same as a BASers, so you can't trust that's what register 13 is being used for. Similarly, register 15 is not necessarily the entry point address. So basically, you can't expect to trust any register values on entry, except register 4 can be trusted as a parameter pointer when parm1 or parm2 is coded on the etdef macro, which defines the PC. So rarely are services designed to expect a single pointer to a single parameter. It's more likely to look something like this: multiple registers pointed to things like control blocks, character strings, or parameter list addresses. And let's say a parameter list might contain pointers to other storage areas that you cannot trust them either. So in addition to making a safe copy of this main parameter list you see in the middle, you also must do safe copies of the second level parameters pointed to from the first parameter list. And similarly, here's a third level parameter area here that you would need to make. So all the way down the chain, you need to make safe copies. The control block masquerade. If your authorized service expects to be passed an address of a control block, making a safe copy of it may not be sufficient because you can't trust it, right? You pointed to something in storage, you claim it's a control block, but it might be something created by a malicious caller, or maybe just a block that is no longer valid. So what you need to do is to ensure it's a valid control block by running independent chain to the block in a serialized manner. So somewhere you have a route that you can go to and chase the chain up the list until you find a control block that matches the one that was passed in. Only then can you trust that that is a valid control block. By the way, we often see code that will check specific string inside the control block that we call an eye catcher. And that's fine if you want to do that, but don't count on that as being an integrity check. After all, these eye catchers could be faked by a malicious caller. So that's why it's important to run the independent serialized chain from the trusted origin. Now, pattern number 5, buffer overflow. Imagine you have a parameter list that contains a length value and a pointer to a corresponding variable length input block. By the way, this is 2 safe copies you have to do here. But you cannot blindly trust the length of the field. Make sure you do a boundary check on the length before you make the second copy. Why? Well, here's an example. In this example, the caller specified input field length greater than what the service is expecting. The caller specified an area this big, but the service was only expecting a block the size of this green rectangle here. But all the data was copied, and we ended up overflowing beyond the intended allocation. And this is a system integrity concern because the overflowed area might represent critical system control blocks or executable storage, and the payload perhaps was malicious code. On the flip side, if the variable length area is intended as the caller's output area, it's equally important to boundary check the length, else risk an overread condition. So in this example, the authorized code trusted the caller provided length and performed a safe copy for something matching the length of their output area. But what it really did is it returned data beyond what was allocated for the service. And that resulted in a loss of confidentiality because the caller may have been able to retrieve sensitive data from this red rectangle area here. Pattern 6, index out of bounds. This is a variation of the buffer overflow problem, and here the caller provided an index value as a parameter. let's say it's an index into a list or an array maintained by the authorized service provider. So let's say the service provider's array, it looks like this. It allows for 3 items to be stored, but the caller specified index 4. He wants this data to go into slot number 4 of the array. So even though you use save copy to copy the data over, the service should have done a boundary check of the index value to avoid altering storage beyond the service's allocated array. Because as we've seen before, we could be overwriting this important information there. So you've got to do the boundary check and be sure to check for negative index values that might result in storage being accessed before the beginning of the array. To recap, we've looked at 6 vulnerability patterns: the unintentionally authorized PC, untrusted parms, untrusted regs, untrusted indirectly anchored parms, control block masquerade, buffer overflow, out of bounds. So the types of vulnerabilities discussed this far can be detected on your system using some commercially available software. I think Brian Childs mentioned a couple of those that are available. We'll now continue to Mike's portion.
Did you want us to pause for questions, Scott?
Oh, yes, I'm sorry. We wanted to pause for questions. Thank you about that. Are there any questions on what I've talked about so far? Put that back up.
There's no questions in the chat. I actually had one.
Okay.
I always get confused by the difference between a PC and an SVC. So my background isn't ZOS systems programming, you see. So I was just wondering is the PC a sort of a modern, sort of newer sort of way to do rather than using an SVC, or they still have their place?
Yes. PCs are more modern than SVCs. We've got a ton of system SVCs that are more or less hard-coded in, and while it's still possible to code additional SVCs, these days it's preferred to code up the PCs. Mike, do you have anything additional on that?
Yeah, there's a lot more room for PC routines, and one other thing is with the SVC, there's a certain registers that the system will set to certain values. So there's only the 4 parameter registers for SVCs, whereas a PC, almost any register could be a parameter, other than if the latent parm is specified in register 4. So there are a lot of differences.
Okay, yeah, because I was thinking that there's that from the security sort of like vulnerability sort of assessment perspective, there seems to be a lot of focus on SVCs, but I kind of get the impression some security people forget about the PCs as well. Yeah,
right.
And PCs can be space switching as well, which is a big difference. An SVC cannot be space switching.
Oh, okay. Yeah. Okay, thank you.
Thanks for asking.
All right. So, like Scott was mentioning, the earlier problems that he was describing are ones that are low complexity, high severity. You could find them with a dynamic testing tool or scanner. The problems I'm going to discuss are more high complexity, low severity, but there are still system integrity problems that could still compromise your system or crash your system, but they're the type of thing that you might find with a monitor or through dump analysis instead, most likely. I organized this so that you can just read them in the future as well. I'm not going to read exactly from the slide, but I have quotes here that I have heard approximately. This quote I have anonymized or removed some of the details. I'm not going to go into whether these are from customers or vendors or IBMers that have told me these things, but they are approximately the sentiment I have heard on some issues, and then we'll explain why that's not the right approach and what can be done to resolve it. So let's go to the first example here. I thought they checked the parameter list. So this is where we were talking about PC routines. If you have one PC routine that calls another PC routine, but it passes through the input from its caller onto the other service, what it might not realize there is that the second routine is going to be making certain assumptions about that data. It's going to check, like Scott was talking about, using the key of the caller. Well, if PC routine A calls PC routine B, then the key of the caller is the key PC routine A is running in. So it would access those parameters using key 0 in some cases, or it might see that it was called by a supervisor state program and not worry about using the move with key instruction. So you don't want to make assumptions that when you're calling another authorized program or PC, that it's going to know that it shouldn't trust your data when your own program is authorized. So in this case, the PC routine A, it obtained its own storage, so it could do a safe copy of the caller's parameters and then pass that safe copy on to the other routine, not rely on the other routine to do its job and for it. So, but when you have a level separation like that, it can happen. Another one that has come up, this is a more severe problem actually when this occurs. Why not just add the user input to the command? You have this network interface, you need to enter a ZOS Unix command. You just need to get one piece of that command input from the user, and then you can just add it to the command and it does exactly what you need. But the problem there is you need to be very careful about syntax checking, making sure you're only getting expected input, because what had happened in this case is they weren't checking for things like vertical bar, semicolon, things that can indicate the start of a new command. So it created a command injection vulnerability by taking that user input and pasting it in there. And then the worst part is then that ran using UID 0. So the solution was, besides syntax checking, using a safer syscall that wouldn't allow multiple commands, making sure that only input in the expected format for that option was actually being used on the command, and also not running in UID 0. The service didn't really need to run in UID 0 instead of its own identity as well. So they were able to correct that before it was taken advantage of. It's in an APF library, so it must be safe to call. This is a common misperception, happens frequently with authorized exit interfaces. If a program allows the caller or the user to specify any exit name that they want, and then, while it's running APF authorized, it will call that exit name. This can create a system integrity problem, because not every program in every APF library is going to be expecting the parameterless format that your service provides to it. The only services that are really required to be able to expect any input will be the ones that are linked AC1, that are supposed to be the job step programs and entry points. Other programs in APF libraries are relying on the authorized program that's calling them to pass them input in an expected format, kind of like in the first example that we talked about. So in this scenario, the malicious user could specify the name of a service it knew was not expecting that parameterless format, leading to a buffer overflow, overwriting a return address, giving the malicious user's program control in an authorized state. So the solution there is to update it to only use expected exit names from an administrator defined list or a preset list, not to just call any program in the system in an authorized state, because that can be dangerous. All right. Why would it matter if the module is reentrant? This is one that is not intuitive, but if you have a service like an SVC or a PC that can run under the unauthorized user's task, and you need to load a program in order to call it, you need to be careful about not loading a non-reentrant module in that environment and then calling it in an authorized state. What happens if you do that is that the non-reentrant program would be loaded in user key, say key 8, and then someone who interrupted the task with a Steimer exit, like Scott was talking about earlier, they could actually at that point from their exit overwrite the executable code since it's key 8 storage. So you don't want someone to do that, because then they just need to exit from their Steimer, resume execution, and now the code they've overwritten will execute. Could update their ACEE control block, could even try to modify the JSCV. It could do a lot of things that you wouldn't want them to do to compromise system integrity. So it's something to watch out for, to avoid. If you have a service like that, an SVC or PC, you don't want to load non-reentrant modules because it can be taken advantage of. So in this case, the module was changed to be reentrant so that it could be called. Another option might be not calling such a program. So keeping on the theme, talking about AC1 and authorized programs, this is a mistake that happens more often than you might realize. People will say, well, we linked our program as AC1 just to be sure. We weren't really sure if it needed to be AC1, so we just made everything AC1 in that load library. So the problem there is that, AC1 means your program can be called as the PGM equal in a batch job, and it will get control in an APF authorized state and be passed a parameter list in the format that a job start program is passed from the initiator. So again, not every module, not every entry point is really going to be designed that way. A lot of them only expect to be called by other modules within your code. So only the job step entry points should be linked to AC1. Other programs should not. If they are, and they mishandle the program, mishandle the parameter list, it could lead to a buffer overflow, could lead to a storage overlay, could lead to privilege escalation. So only link things AC1 if they need to be. Dealing with SRBs, sometimes people will say my SRB, doesn't need a purge TCB or a SID. I don't really think I need to worry about that. But the problem there is if you're accessing any storage from your home address space, or maybe a load module or control block that's owned by the task that's attaching the SRB, if in your home address space that task is terminated, or even your address space is terminated, the storage that's being used by the SRB in the other address space where it's running would then be freed out from under it and could be reused. Even during termination processing, it could be reused, or if the address space is reused, then the storage could be used that way. So you want to make sure that your SRB stops running in that scenario and doesn't execute using the wrong storage. Besides purge TCB and purge ASID, there's also purge Stoken available that's recommended in order to avoid running in that unsafe scenario. When someone writes an ENF listener, sometimes they don't specify the EOT or EOM option. That's short for end of task or end of memory. But those options are important when you have an ENF listener for very similar reasons to what we were talking about with SRBs, that if you're relying on data, you're relying on storage, that will go away if your address space goes away. So you don't want that to happen. You want to make sure that the ENF listener is not called, is not executed, since it will run as an SRB when those conditions occur. So updating that to add EOT and EOM will stop it from running after task or address space termination. If they use force arm, it's their fault, not ours. Sort of playing on, well, they forced our arm, right? We had to cause the system integrity problem. But in this scenario, someone waiting on an ECB, for example, the address space is forced, things are not cleaned up correctly, ECBs are posted after the storage has already been freed and reused. You really need to be able to handle the worst case scenario. When the code is running in system key or authorized state, you don't want to be overlaying code causing system integrity problems during termination. So in this scenario, termination processing was updated to avoid freeing storage while it was still being used. This is the classic use after free scenario, one of the very common integrity problems on any platform, as well as on z/OS. We get the storage, so no need to check the size. This is especially an issue with space switching PC routines, where the caller is in one address space, but the PC is running in primary in another address space and obtains storage in that other address space, usually a started task. So when the caller specifies a size, perhaps of how much data it wants to be returned, the target routine, PC routine, might just blindly get as much storage as the caller asks for, up to the maximum allowable in the address space. And the problem with doing that, with not having any limits or constraints, is that through trial and error, they could ask you to allocate all of the available private storage in your address space, especially if they're able to run a few jobs in parallel. So then they could interrupt their task with a timer again, or just keep calling this in a loop. And they could effectively block anyone else from using your services, making your service unusable, causing a denial of service. So in this case, PC routine was updated to do a sanity check on the size in order to avoid having that vulnerability. Won't the system initialize that to 0 anyways? Yes, the uninitialized variable, the uninitialized register, the types of things compilers warn you about, but as long as it works, programmers don't always worry. But when your program is recompiled, the compiler may make a different decision the next time, or some of your assumptions about the layout of the storage or the allocation of the storage, the way it's initialized. You don't want to rely on residual data and storage performing in a expected way. You want to correctly initialize your registers and variables, because what can happen is that might occur in a predictable way. It might suddenly start using a value and overwriting a certain address or branching to a certain address, and that's where someone could then take advantage of that. If it varies between systems, maybe on your system it's fine, but on someone else's system, that residual data causes a problem. So, and this is fairly basic, but initializing data registers can prevent security vulnerabilities as well. We can't get serialization due to performance. A common complaint, the trade-off between security and being able to do things quickly. Sometimes doing extra security checks or gaining serialization can slow you down. We had a example where someone had an authorized program. It was scheduling SRBs to try to monitor certain things in other address spaces. Wasn't getting serialization at all, and then it was printing out the data to a report. So the problem there is, again, the use after freeze scenario ends up reading some storage that isn't what it thinks that it is, and then printing it out into the report. So an especially bad example would be, user ID / password, for example. It's somewhat independent of the context. If you see a pattern like that, then you may have just got some sensitive information. So the solution here is first to get serialization, or if that is really not possible in the scenario, to have additional checks there to make sure that the data, before you're writing anything out, is valid data and is what you expect that it is. When you're running under an SRB, you don't have to worry about getting interrupted, but because you have that authority, you can, when you're running system key, accessing authorized data, you do have a responsibility not to reveal that to unauthorized users. So some of it there. We need to display all that data for diagnostics. And this one I sympathize with. Getting diagnostic data to help debug problems and help analyze what's gone wrong is a good intention. However, if a recovery routine assumes that register 13 is going to be pointing to a valid save area chain, regardless of how it got control, that might not be a good assumption. Usually routines will call other programs. Those other programs may not use R13 for a save area all the time, or they may call other services. So when your recovery routine gets control, that you really can't guarantee that register 13 is going to point to valid data. So then if you go back and try running the save area chain, you may end up displaying in your diagnostic messages data that is not intended, especially if you're doing that in system key. So one solution is to use the user's key, like the TCV key, to avoid displaying data that the user is not authorized to, or to check like the PSW range, make sure you're really in the area that you think you are where the register 13 is safe, and avoid displaying data that shouldn't be intended to the user. Another option is just to get a system dump and not try to display the data to the screen. And then someone would have to be authorized to view a dump in order to see diagnostics. All right. No one ever complained about that program yet. People wonder, if it's not broke, why fix it, right? They haven't seen an issue yet. But the problem with system integrity is that if someone discovers a vulnerability, they may not report it. They may just figure out how they can take advantage of it and hope that no one else discovers it either, right? And so when people are complaining about a problem, it gives us the opportunity to fix it. But if no one's complained, we may have missed it till now. So in this example, a fairly obscure problem, started task missing null pointer check, but occasionally what it was referencing in low storage on the system would actually point somewhere that it could end up overwriting data. So you don't want to have on your system overlays of system key storage. Even if an end user may not be able to control it, they may be able to take advantage of it, or something unexpected may occur on your system, just violating the system integrity of your installation. So you really want your authorized programs to execute in controlled ways. So in this case, the fix was simple. Started task was updated to check for 0 and avoid referencing unintended storage. It recovers from the AVEN, so it's not vulnerable. So here they said, not just that no one ever noticed it, but that, oh, the program took care of it. You don't have to worry. We recovered from that. There's no vulnerability. But when we deal with a program check analysis for security vulnerabilities, we're really worried about what happens if it doesn't AVEN, right? Like if it's really referencing something that will always fail, it may not be a problem. But if suddenly it might actually overwrite something or branch somewhere, that's where the integrity problem occurs. So in this case, module, was extended, like, additional code was added. New base register was specified. Recovery routine forgot to reset the new base register. So it was doing some crazy things, might overwrite some storage. But usually even when that happened, the other recovery routine before it was, cleaning up enough that it didn't really surface the problem. So they didn't think it was an issue, but overwriting of storage, branching somewhere unintended, can definitely be an issue if someone notices that and finds a way to take advantage of it. So here the recovery routine was updated to restore that base register correctly and avoid those unintended consequences. Isn't everybody using AMODE 31, not AMODE 24? Well, there are a lot of, for compatibility reasons, there are a lot of things that still allow or support AMODE 24. So in this example, there was an exit and it was checking the AMODE bit to determine how the program that was calling the exit was checking the AMODE bit to determine how to call the exit in which AMODE. The authorized program specifying the exit address forgot to set the higher bit. Therefore, the address was truncated. It's called an AMODE 24 and leaving off the high byte of the address, branching to an unintended location in private storage, where someone could simply figure out how to place their own program in that location. If this was a service that could run under an unauthorized user's address space, and then they would be able to run whatever code they want in the authorized state by tricking the system into calling, or the service into calling that code of theirs instead of the intended exit. So the fix here was simple, turning on the higher order bit, but taking into account AMODE considerations could have avoided it in the first place. The post to the missing ASID should safely append. That sort of along the same theme of, well, why worry, it'll just append harmlessly. But when you're posting another address space, specifying an ASCII, that's really not the way that you want to do a cross memory post, because that task or ASID could be terminated, could be replaced by another address space. The SRB for post could still run there and try to update the ECB, but it's no longer the ECB that you thought that it was. So that's why the SafeXM post service was created, IEA MS XMP, and that should really be used to avoid that problem when you're doing a cross-memory post. It uses a token, make sure that where you're posting is where you intend, and avoids more unexpected or unintended overlays that someone could take advantage of. Then the last example I have is a trickier one to solve, but I have heard this before. We need to free that code to avoid a common storage leak, and that is true. That if a service is obtaining common storage every time it starts or every time it runs, that could create a common storage leak. But on the other hand, if you are putting code in common storage that way, then usually that's because people in other address spaces could be executing it. So you don't want to just free code out from under something that could be executing in an authorized state. It could be replaced with something else, either through manipulation or chance. Then that could be taken advantage of, especially if someone noticed it happening in a repeatable way, figured out a way to call a service that would then end up leading to a privilege escalation. So it can be dangerous to free code that exists in common storage while it's used. Some alternatives are to anchor that program from a control block that persists, and then you would simply keep using it in the same location. There's two ways to do that: through control blocks like the CBT, or through the authorized name token services, which are available as an alternative. The reason that you really, some people will say, well, we need to update our code. We need to apply service or maintenance. We don't want to have to IPL to do that. Well, a solution to that would be to provide an option. So when your service is starting, maybe there's a refresh option, and it wouldn't always use it, but when it does need to be used, then maybe you would get a new copy then, and you start using the new copy while still leaving the old in place. That could limit the scope of the storage leak without introducing a system integrity problem, which is the goal. So I covered a lot of different complex scenarios, and him talking about them at sort of a high level, but these are the types of problems that can occur when you have authorized code, and you need to watch out to make sure you're doing things safely and not adding those risks of security vulnerability to the system. So let me pause there if there's any questions on that section, and then I'll let Scott.
Okay, thank you, Mike. I'm having
yeah.
with my connection here, so sorry.
Oh, someone sounds like they're having a bit of difficulty with their voice. Is that Scott?
Yes, it did. Okay, sorry about that. We have a page of links to some interesting things. We got the system that we mentioned at the beginning. The link to the Z Security Portal FAQ. No, can you hear me?
Yeah, I can hear you now. You were a bit robotic at the beginning. You were breaking up a bit.
Microphone might not be.
Sorry about that.
You're good now.
I think it's my machine. Yes.
Don't worry, I've had gremlins with my headset today.
So interesting links. And the last one is the Authorized Assembler Services Guide. So I think I better be done.
No problem. Thank you so much. So I did have a question. So my take from this, like I said, I'm not a ZOS systems programmer, and a little confession here. So when I was about 20, when I first started off in IT, I was given an assignment. I had to learn. I was told, right, you need to learn COBOL, you need to learn Rex, you need to learn SAS. Although you got to learn assembler as well. And I wrote one piece of code, and it moved into some something into a register 15, I think. And when you were talking about registers, it's kind of like, so yeah, that was my sort of my journey into assembler, and that was it. It ended there.
It sounds like setting a return code, perhaps.
But yeah, I think that was exactly what it was. I was trying to remember what it was. It was so long ago. Yeah, exactly. So I did it, and then so I, but my takeaway from this is, so a lot of code validation needs to happen, right? To like both in the unauthorized, the caller and the authorized program. Is that correct? That we need to make sure that these things are, behaving themselves and not overstepping boundaries and so on.
Yeah, there's a lot of gotchas and not a lot of like code analysis tools, for example. Though they're like other people have talked about in the there are code scanners, code monitors, and I don't think I'm supposed to talk about IBM's products in particular, but they're
no, but yeah, I know. And that was actually going to be my next question, because it's like when we sort of like look at the validation and stuff. Of course, the other really important thing is that you do code scanning. With the different vendor solutions that are out there, shall we say. So I suppose that's the sort of next important thing, as well as the patching, as well. Any sort of fixes that come out in the security portal, and just making sure you really understand exactly, regardless of who wrote it, that you are absolutely confident that it's not going to mess with the integrity of the system. Is kind of my takeaway from what you guys have talked about today.
Yes, it's easy for them to make a mistake. Like Scott said, one line of code that can compromise their system. And that's why in the security portal, all the types of problems we were talking about would be a security vulnerability posted with a fix in the security portal to be updated for customers. And you want to keep up with those fixes from vendors as well.
Indeed. All right, guys, thank you so much. It was a brilliant session. I've learned quite a lot from that, and I'm sorry about the low attendance. By the way, it's not wasted your time here today and the effort that you put into your presentation, because this is being recorded and it will be available for for on-demand viewing. So rest assured, where all of the content does get a lot of hits. People can't attend sessions. And so they will listen to them on demand at their leisure. So thanks so much for taking the time to do this. And for those that are still on, and for those that are listening on demand, that the session code for this is 8R. So even once the conference is closed, you can still leave feedback. So please do that. And any backlog that you've got for previous sessions that you've attended, whether you're listening to them live or on demand, make sure you do that. Presenters want to hear your feedback. And also we do at GSE, and the most important thing for the attendees is that that it counts towards CPE points if you're collecting those for your certificate. And one final word on that, because we get asked this question quite a lot: if you want to get your CPE certificate, if you've got credentials and stuff, and you need the evidence that you've attended, you go to My GSE, and then if there's a drop down from there, and then you'll be able to download your certificate, not just from the virtual conference, but any previous conferences that you've attended where, but the trick is you've got to have left feedback for those. So that's it for the security stream for the virtual conference for this year. We will be back in November for the in-person conference, and I just wanted to say a big thank you to obviously all the presenters, including you, Mike and Scott. Thanks for I know it takes so long to put together a session, and the presenting is done so quickly, isn't it? But it's hours and hours and hours of effort and preparation. So thank you to everybody who's contributed. And I want to say a big thank you to Sue Parsons, who's been my co-pilot for the last throughout this conference, as she's with me for all the conferences that we do in the working groups, helping out. So thank you, Sue, for all your help there. And that's it. So we'll close the security stream, and right up next in 2 minutes' time, we've got the closing keynote that we've got to jump onto, and that concludes the conference. So thank you very much. Take care, everyone. Thank you.